So today we're talking about relationships between two variables. And usually the reason why you're looking at a relationship is that you're sort of probing for causality. You're wondering if one thing causes another thing. And there's a standard bunch of different standard terminologies that we use in these situations. In our textbook, we use the thing that is doing the causing, we call the explanatory variable, and the result or the effect is the response variable. So those are the words you're going to see all the time. You can also use different words, and there's, of course, cause and effect. There's independent and dependent, input and output, driver and outcomes. So whatever terms we use, there are four possible types of analysis depending on the types of the two variables. You could have both being categorical. You could have the explanatory being categorical and the response being quantitative. You could have a quantitative explanatory and a quantitative response, and you could have a quantitative explanatory and a categorical response. In this course, we're only going to really deal with the first three of those four situations. The last one really gets difficult mathematically. Okay, there's causality is difficult to determine. And here's if you think that something called A, the explanatory variable, causes something called B, the response variable, there are really four possibilities. First, A really does cause B. But the second, and there's really no way to distinguish the second from the first using statistical methods, is that B causes A. And then there's C, which is unobserved, causes both A and B. C is what we call a lurking variable. It's lurking because you don't see it. You haven't bothered to record it, so you don't even think about it when you're doing your analysis. And the last possibility is that when you're looking at what seems to be a relationship between the two variables, it may be that this is just something that is the result of random fluctuations. And that's the situation that statistics is really well designed to deal with. We can kind of look at things and say, yeah, that happened, but it's the relationship is really very, very weak if it's there at all. Okay, so I've got some things for you to think about and look at with these things. And for each of these situations, to identify the explanatory variable, the response variable, and the type, categorical or quantitative, of each. Of course, which is the explanatory or which is the response, it's kind of up to you. So read through these things, write down I'd like you to write down your answers. It would be a really good idea to commit yourself. And then after that, there is a separate video. Click here. And by clicking, I mean right-click and select Open a New Tab or Open a New Window. Okay, so that should take you about 15, 20 minutes, and you might want to stop this video and do this right now. Yeah, I think it'd be a good idea to do this right now. Okay. So if you've stopped the video and done this, follow this thing up, as I say, right-click and then open link in new tab, and you'll get to my video, my YouTube recording of this thing. Okay? Second thing, I've got some following observed correlations and causality conclusions. Comment on why the observed correlation might not imply the suggested causation based on only the first three of the four possibilities listed above. Someone observes a strong correlation between height and reading scores. That's kind of surprising. People who drink red wine tend to live longer. People who live in zip codes with a population that has higher levels of education have higher incomes, so higher education leads to higher income. People who switch from other auto insurers to Geico save a lot of money compared to those who don't switch. This is one that always kind of amuses me. Anyway, write down what you think of all these things, and then follow up by clicking here. And again, it's right-click and then open link in new tab or open link in new window. Okay, so the first these cases that we're going to look at is a categorical explanatory and a categorical response. And this is based on a thing published by Open Intro. It's a good case study. You can find it here. I hope this is still here. And I've got the data is actually available in Canvas if you want to look at it. And after I've loaded the data frame, which is called Stent 365, I do an str. str is the standard command for structure of something. What is it? And it says that it's a data frame with 451 observations of 2 variables. So every person in this thing you've identified with 2 different categorical variables. There's the group, whether this person was a control subject or a treatment subject, and an outcome, whether there was no event or a stroke. This is a really important type of study. It's a random controlled trial. It's the only type of stuff where you can really establish causality. And the way it's done, you take a bunch of people who are all basically the same, and in some cases you give them a treatment, and in some cases you give them a control. And of course, the people must not be aware that they are either treatments or control. And here's the key command you want to use in R to analyze the relationship between 2 categorical variables. It's table of Stent $365 group, comma, Stent $365 outcome, and this is what we get. The controls, there were 227 of them. 28 had strokes. The people who got treatment, there were 224 of them, and 45 got strokes. This is not really looking good for the stent outcome. There's another table command that you can use which gives you a lot of detail about the data in the table. This is a very skinny, very stripped down table, and if you run use the cross table command from the gmodels package, and you run cross table, the same 2 variables, group and outcome, you get a very, very complete breakdown of the data. For instance, you can see that there were 227 controls. It added up the 2 columns for you, the 199 and 228, so you didn't have to do the arithmetic. And then you see that the third number down is the n divided by the row total. So it says that 87.7% of the controls had no event, and 12.3% of the controls had a stroke. You look down the corresponding numbers according to this little decoder box up here. It says of the treatment, 79.9% had no event, and 20.1% had a stroke. And you can see this is why I say that this is not really looking good for the treatment, because the 20.1% of the treatment people had strokes, and only 12.3% of the control people had strokes. It appears that the stent actually is doing increasing the probability of having a stroke. Although this is just a really sort of casual look at it at this point, we're not doing really a formal test of hypothesis, which we'll get to in Model 8. Okay. Now these are the two commands that you could use to look at the relationship between two categorical variables numerically. Graphically, we take a table, and in this case, notice that what I've done is not just displayed the table, but created the table as a named object called George. And then I did a mosaic plot on George, and I added the extra option to give it a title main equal plot of group by outcome. And it is then clear that we sort of had to do arithmetic of one sense or another, or look through a table to look at the numbers. But when you do the graphical outcome, you can see that it's the height of the stroke outcome in the treatment column is much greater than the height of the stroke outcome in the control column. So really you're comparing these two. There's another set of data which is also sitting there for you in Canvas. And if you perform the same type of analysis on the depression data, and what you're considering is whether the different hospitals vary in their treatment choices. Okay, so create output similar to what is above and think about what it's telling you. It would be a good idea for you to write down your observations. Then after you complete these tasks, watch the data, or watch the video, which I've produced to explain what I see in this thing. Okay? So that's categorical variable and, well, two categorical variables. One is the response, one is the explanatory. Now let's turn to the second case, a categorical explanatory and a quantitative response. And I'm using the MT-CARS data frame, which is built into BASE-RS, and you don't have to do anything to get access to it. It's just look at it. So I run the structure command on MT-CARS, and I see that it is a data frame with 32 observations of 11 variables. And this is taken, I think, from Road and Track in the early 1970s. So some of the technology may be sort of alien to people in 2025. For instance, the number of barrels in a carburetor. There's a 4-barrel carburetor, 1-barrel carburetors. I don't think anybody has a carburetor anymore, except maybe on a chainsaw or a lawnmower. Okay, but anyway, back then, 50 years ago or so, this was an important thing to think about. Everybody had a carburetor or a couple carburetors. And then I do a summary of the data frame to look at it, and I see that miles per gallon goes from 10.4 to 33.9. Cylinders go from 4 to 8. And there's a lot of 6-cylinder vehicles. And I think all of this stuff pretty much makes sense to anybody who's familiar with motor vehicles, except maybe for one of the variables which we're going to use, AM. AM is categorical, even though it's coded numerically. Either it has a 0 or a 1. Those are the only two values that you have for AM. And it's 0 if the vehicle has an automatic transmission, and 1 if the variable has a manual transmission. So that's the categorical variable we're going to use for this analysis. And for the quantitative variable, we use MPG. So what I'm looking for is there a causal relationship between the type of transmission and the type of, not the level of gas mileage that you get. The numerical way to look at this is to use the tapply function. And tapply has three arguments. One is the variable that you're trying to analyze or get descriptive statistics for. The second one is a categorical variable. It's the breakdown variable. That is, I want the values of this thing broken down by this thing, and then the function that I want to apply is summary. So here's the summary data for the AM values of 0, okay, which is automatic transmission, and I see that I have a mean MPG of 17.15. For the stick transmissions, I have a mean value of 24.39. So it just kind of on that simple comparison, either median to median or mean to mean, it looks to me like the stick shifts actually get better mileage. Okay, well, I'll have to say that I can't really reach that conclusion because of one of the problems you always have when you're doing observational analysis rather than a controlled experiment is that there are other characteristics which are associated with having a stick shift. Back then, a stick shift means that you have a cheap car, which is typically very small in weight and very small engine. So what you may be seeing, which is the stick shift, is the impact of having a lightweight car with a small engine. It may not be the characteristics of the transmission at all. To do an honest look at what the transmission does, you have to somehow take a bunch of different models of cars which are exactly the same in every respect, weight, the engine displacement, everything, and try a stick shift version and an automatic version. But that was not the way this was done. This is just observational data. Okay? So this is the numerical way to look at a relationship between a categorical and a quantitative. Graphically, we want to do a side-by-side box plot. So I do a box plot, and the first variable is the quantitative variable, tilde, and the tilde is the character on your keyboard right underneath the escape key in the upper left-hand corner, and it's the uppercase key. Sometimes people call this a squiggly. So here I have on the horizontal axis, I have the type of transmission. Here's the automatics, here's the stick shifts, and I can see that even the 25th percentile of the stick shifts is higher than the 75th percentile of the automatics. Okay? And again, this just leaps right out at you when you look at a graphic display of data. Okay, the final thing is the relationship between two quantitative variables. Quantitative explanatory, quantitative response. And my theory is, of course, that there's a causal relationship between engine displacement and miles per gallon. The bigger the engine, the more miles per gallon, or the fewer miles per gallon you're going to get. And the first thing I do graphically is to look at what we call a scatter plot, and it's just plot of variable 1 comma variable 2. And in the first position, when you're creating a scatter plot, you want to put the thing that you think is the cause. Okay? And the second thing is the thing that you think is the effect or the response variable. And yeah, I see what I expected. Namely, I see that as engine displacements gets bigger, gas mileage goes down. Okay? In fact, I think I see sort of, it's not a perfectly linear relationship. I see sort of two segments. There's this area here between 100 and 200 cubic inches where you've got a very steep decline in miles per gallon, and then the second segment between 200 to about probably 500 cubic inches where you get a less of a steep decline. The correlation coefficient is the numerical, one of the two numerical ways that you look at this, and I get a negative 0.84. And you should realize from what you did in the last part of the Module 2 readings in the OLI material is that negative 0.84 means that you've got a pretty clear negative relationship, but it's not, of course, a perfect relationship. If I had a negative 1, that would mean that all those points were right exactly on a straight line, and the straight line would be going down. But I don't get a pure negative 1. What I get is negative 0.84, which is a really strong negative correlation. Okay, we're going to go a little bit deeper with the two quantitative variables. And you all remember y equal mx plus b, I hope. Well, what we're going to do is we're going to try to create a linear relationship between displacement and miles per gallon. So instead of y equal m times x plus b, it's mpg is m times displacement plus b. And in order to get the best possible fitting line to the data we've got, you need a procedure which will give you a value of m and a value of b. M is called the slope, b is called the intercept. And the procedure in R for doing that is called LM, linear model. And it's linear model MT cars $MPG tilde MP cars $DISP. This is the explanatory, this is the response. So it's always response tilde explanatory. And I name my object something. I named this object Sally, and I did a summary of Sally, and get a whole bunch of gobbledygook out here. And the M and the B are to be found here in the estimates column. And the intercept, the B, is this thing, 5.99855, and the slope is here. It says it's the slope of displacement. It's negative 0.04. Okay. So I'm going to show you what happens. We can use that equation that we've developed now. MPG is m times displacement plus b, and we can create a miles per gallon for a vehicle with a 200 cubic inch engine. The equation says that that should be 21.35. And then I can also do the same thing for a 201 cubic inch engine and print out that value. And then if I look at the difference between the two, I can see that I get this thing, which is the same thing as this number. In other words, the interpretation of the displacement, or the displacement's slope, is that an increase of 1 unit in displacement causes a reduction in gas mileage on average of negative 0.05. 0.04. Another way that you could say this in sort of numbers that might make more sense is that if I add 100 cubic inches to displacement, I would expect my gas mileage to go down by a little over 4 miles per gallon. That kind of makes sense. And then I did another plot, repeated the plot that I'd done above, and then I used the command AB line of Sally, and that says stick the linear model, the line defined by our model, into the graph, and I can see, yeah, this is the way it fits. Okay? Okay, so that wraps up everything I wanted to say about the Module 2 notes.